Okay, hello everyone, welcome back. In this video, we're going to present the next iteration of the algorithm that we were implementing. In this case, the two-qubit variational form. So the implementation is going to be slightly more complex, nothing really too difficult. In this case, we are going to extend our previous example to 2 qubits. The idea is that by doing that, not only we will need more additional gates to cover the second qubit, but also we can start to consider entanglement between the 2 qubits and multi-qubit gates, basically. So by doing that, we can start to use as a really simple 2-qubit gate a CNOT. In fact, we will use several because this is something that is going to give us more flexibility in terms of interdependency between the 2 qubits, and also in order to modify, adjust any behavior in between before we implement the next CNOT down the line, we will also need to start using more universal gates in between. So with all of that, what you are seeing on the screen now is one of the possible implementations of a 2-qubit variational form. Is not the only one, of course. You can think of other designs. In this case, the design that we are using is what is called the minimal universal 2-qubit quantum circuit or variational form. The idea is that it comes from that paper that you can have a look at. Is a 2-qubit variational form that is universal, that can cover and can potentially implement any quantum circuit, quantum state. Sorry, I just noticed I was in between. So yeah, that's the idea, and you can see on the right a possible example. So the next thing that we will do is that we will take the code that we implemented in the last iteration and the last video, and we will expand on that. We will start to consider a more complex case, some of the functions that we implemented. Let me go to that. Yeah, some of the functions that we implemented were quite generic and won't need any type of modification. Some others, now that we increase the number of qubits from 1 to 2 and the number of potential classical states from 2 to 4, 2 to the 2 to the power of 1 and 2 to the power of 2. With all of that, some modifications will be needed. So actually the libraries that are being used are exactly the same. The final notebook will be available in Moodle. And what you can see here is basically the previous implementation. So yeah, no issues there. And the idea is that we will start to review each one of these functions in order to understand whether there's something that should be modified. And let's start with these two first functions. So if you remember from the previous content, the plot probability distribution function basically takes a probability distribution, which is a vector, and it should be normalized, and then it basically generates this plot. But this one here, if you have a look at everything, is based on 4 loops. It doesn't really have any limitations, it's normalized. So actually we can provide also a vector with 4 classical states and it won't be an issue. In this one here, we were talking about creating a random probability distribution. Now things are a bit more complex because we don't want a probability distribution with only 2 possible values, but instead we want to start making this more generic. So the number of classical states associated, the number of possible classical states associated to a quantum register is 2 to the number of qubits. So we need to include the number of qubits. In the previous example, this number was 1, so the 2 to the 1 was 2, basically. But now that we are starting to make this a bit more complex, we need to increase this value. The rest remains the same in the sense that we still have to normalize everything. And here the only difference is that previously we were working with a number of qubits of 1. Oh, sorry, I have to execute everything because I stopped the Jupyter notebook. Also, reviewing the list, I don't think we used assemble. because I think this is something from a previous version of Qiskit. This is really fun because, as you know, this changes every year. So yeah, we are no longer using assemble. I will remove that from the final version of the notebook. Uh, Here's the IBM token and the two functions, and let's see the result. Let's see if this works. I tried it only for 1 qubit just to make sure that it remains functional, and then we will increase this to 2 qubits. I think it's still connecting to IBM, so it will take a second. Okay, there it is. And the probability distribution. This is for 1 qubit. If we increase this to 2, it should be able to show probability distributions for 2 qubits. If we consider 3, yeah, seems to be working. Okay, so in this implementation, we are going to stick to 2 qubits for classical states. You can notice how they are labeled in base 10, basically. Okay, build variational form. This is the 1 qubit variational form that we considered before. In this case, it's going to be a bit more complex. So if we go back to here, you can see that is basically 4 universal gates and per qubit, and in between we would use control NOT gates that will be applied on 1 qubit, then the other, then the first one, and so on. So with that in mind, let's go back to the implementation. Yeah, basically we're going to expand this. So let's start by increasing this to 2 qubits. We build the quantum circuit. The measurement will still be needed, but everything in between is going to be a bit different. In this case, the set of parameters here doesn't specify how many parameters do we have. This remains the same, so we will apply a universal gate to the first qubit and then another universal gate to the second qubit. The thing is that this set of parameters is not the same as this one. Each one of them needs to be different so that we can modify each individual parameter independently of the others. So by using 2 universal gates, we already have 6 parameters. And then, as we saw in the picture, we will need a controlled NOT gate qubit 1 and qubit 0. And then this block, basically, this block here is repeated 4 times. And we need 3 controlled NOT gates in between. So that let's copy this a few more times. We can remove this last control NOT. Okay. And also we need to make sure that each individual parameter is different. So we were at 5. Let's do 6, 7, 8. You can skip this part. 9, 10. So in this case, we need 24 parameters from parameter 0 to parameter 23. You can see how this can increase exponentially as soon as we want to consider universal variational forms for a higher number of qubits. So the idea is that once you start to make this a bit more complex, you will see that in the literature they will start to use specific variational forms that will have some additional knowledge about the problem at hand, making things a bit more efficient. This is universal, so this can actually be used for anything up to 2 qubits, of course. We need to modify the second synod so that it's applied on the opposite qubit. Okay, there we go. So that's the universal form that we were presenting. Then we have to review the method, measure probability distribution. In this case, there's one additional requirement. We're going to create a variational form here, and for that, well, it doesn't matter here because the number of 2, transpile circuit, execute route, here this could change, and there's something additional here because we need to adapt the format also. So this is no longer true. Oh, give me a second. So basically this is no longer needed, but in this case we need to review this right here, and also this is going to be expressed in terms of binary labels, so we need to convert that. So those are the counts. We're going to generate for I in range Okay, so basically we are generating the binary labels, and these binary labels need to have a common length that is equal to the maximal possible value. So if we are working with 2 qubits, that means that we will need 4 classical states in order to encode the highest value of that, which is basically 3. We need 2 classical bits. Makes sense after all, because it's the number of qubits is 2, the number of classical bits is 2, and actually you can see that here. So we need to make sure that all the labels have that length of 2 and are expressed in binary, basically. So because that's how we will find it. So now that we have the binary label, we are going to check if that case exists in counts. If not, we will need to add it. So basically this method, the purpose of it is that whenever one of the cases is not available, this will make sense that we specify explicitly that for that specific instance there's no number of shots found. This should also ensure that all the different classical outputs are considered. So that's covered, and I think that everything else remains the same. The only difference is that here we need to specify in measure probability distribution. We are going to need the number of qubits, I guess, because it's here, it's been used. So we will need it. That makes us have to use it here. In terms of parameters, we need 24. So let's just pick 0 24 times and 1 24 times. This is just to show a few examples and make sure that everything works up to this point, because there's always some typo. Number of qubits, let's just specify it right here because this is just for testing. Okay, so for 0, when all the parameters are 0, you can see that in the end we are not affecting anything, and whenever it's all ones, then that means that I could modify these labels. That means that this is the possible, the possible no, it's the example that we would find if everything were to be set to 1. Okay, so now let's review the compute cost function. I think this is going to remain the same because in the end it's generic. Having the output and the target is just the absolute difference. Yeah, that's going to remain the same. And then we have the optimization. The idea is that create on the probability distribution, this is going to need the number of qubits. Then we have the plot, optimize, the optimizer, parameters. In this case, we need 24 parameters because that's the number now. Output distribution measure parameters backend. This is going to be getting the number of qubits if I'm not mistaken. Compute cost, that remains the same. Optimizer minimize. Result.x, cost, return parameters and cost. Okay, here we will need the number of qubits again. Plot probability distribution. Yeah, I think that's it. Let's see. We will run this a few times just to check how everything works. So this will start to get a bit more complex in terms of number of parameters. It's not that bad. I mean, in some cases, I have to say that the reference is higher, but in this example, it did pretty well. It depends. I mean, as we mentioned before, there's a lot of variables, and that's going to affect the result, but it's doing pretty good in this example. I want to find one that is a bit more different so that you can see what happens in some cases. So yeah, I mean, you can apply some strategies similar to classical, this could be a good example, similar to classical machine learning. You could, for example, put this inside another loop that initializes the set of parameters and everything else a few times, and then from different possible configurations of those parameters, depending on where everything was initialized, you could pick the best result. So that would be another loop on top of that. You could try for a few initialization settings, maybe 10 different configurations, and that could be a way to ensure that it's a bit more reliable. I mean, it's working well in some cases. In others, you can see that it's not as good. It's quite common to see that the distribution is not perfect. But yeah, that's more or less the approach. Let's see this last one, and with that, we will close. In the last, In the last chapter, we discussed the 1-qubit variational form. This is the 2-qubit variational form. And with that, we have covered the 2 examples, and we will now move on to a more complex scenario in which we implement the variational continuity solver with an actual use case in mind. Thank you so much.